Here we go. Two-dimensional momentum. Momentum doesn't, nothing here really changes other than the fact that we're going to start adding the vector notation that we used for dynamics to momentum, which might be a big difference. I don't know. We'll see. You tell me how you feel about this at the end. So the reason we can do this, velocity is a vector, momentum therefore is a vector, velocity has direction. We can look at velocity direction in 2 dimensions. We could do it in 3 dimensions, but we're not going to. So we can look at momentum in 2 dimensions, which we could also do in 3 dimensions, but we're not going to. This means that the impulse equation can also be expanded to be dealt with in multiple dimensions. Net force is a vector. Initial and final velocities are a vector, so we can add these things like we were before. We can use addition of vectors, adding vectors tip to tail, using the sine law and cosine law. We could break these things up and look at adding components together. All of those procedures that we've done before are going to show up again. So let's just get into it. We've got a 2 kilogram object moving at 5 meters per second, 20 degrees west of north. Now, I do recognize that I need to do a bit of a review on what west of north means. Okay, north and south typically are up the page and down the page. East is typically to the right. West is typically to the left. So west of north means you start at whatever the second direction is, and you go the first direction, that far. Basically, you're reading right to left. From north, we go west 20 degrees. And the reason I know that I need to go through this is because I finished marking all your dynamics tests. So 20 degrees west of north, start north, go west. We want to find out the momentum vector and its components of momentum. So the momentum vector, we can deal with this a couple different ways. Let's do A and B. The momentum vector will be A, the components will be B. So when it asks for the momentum vector, the name we had for those kind of coordinates was polar. Polar coordinates is just going to give us the vector, and what we want is the length of that vector, also known as the magnitude, and the direction using degrees. Those of you who are in calculus, make sure that your calculators are not in radians when you're doing these things, because it'll go poorly for you. So, we've got that. This thing weighs 2 kilograms. It has a velocity of 5 meters per second, 20 degrees west of north. Momentum is just a scalar times a vector. Mass has no direction. Velocity does. So P is just going to equal M times V. So that's just going to be 2 times 5. And the direction doesn't change. 20 degrees west of north. So this thing then has a momentum vector that is 10. And we need the units. There's a whole bunch of different units we could use, but I'll just use the easy ones. Mass is in kilograms, velocity is meters per second. So momentum is kilogram meters per second, 20 degrees west of north. Relatively straightforward, yes? Multiplying a scalar and a vector together, directions don't change, is the nice part of that. Because the hard part's not momentum. The hard part's going to be looking at change in momentum. That's where things are going to get dicey. So part B says it's components of momentum. So we're going to take the momentum vector and we're going to break it up into components. So we've got, this is our momentum vector. P is equal to 10 kilogram meters per second, 20 degrees west of north. So that there is 20 degrees. For the sake of my picture and to help you guys review some stuff, I'm going to draw this as my component triangle. We're going to start at the base here, and I'm going to go to the left. I'm going to have my px component first. and this is going to be my py component. If that angle there is 20 degrees, what is this angle here? 70, because those angles add to 90. So then I'm going to have px is going to equal 10 cos 70, almost. What else do I have to add here to my px? It's going to the left. So we know this vector is going to be negative, so we have to put that negative sign in there implicitly. Py is upwards, so we know it's going to be positive. That's going to be 10 sine 70. Zach, you're cranking out values? Oh, was that what you were doing? Okay. What's the next digit?
9.39.
Okay, so that one's 9.39. This one's 3.4 what? 2. Okay. Kilogram meters per second, kilogram meters per second. So that's the x component and the y component. So I can write this out using the other notation that we use. Does anyone remember what we used for that notation? I hats and j hats. So I can say that my vector p, which in polar was 10 kilogram meters per second, 20 degrees west of north, is also going to be equal to negative 3.42 I hat plus 9.39 j hat kilogram meters per second. And we're done. So we've got an expression for our vector in polar, and we've got an expression for our momentum vector using components. This is going to be useful if you guys are comfortable using sine law, cosine law, addition of triangles, or addition of vectors to create triangles, finding resultants. If that is something, if that just makes you uncomfortable for whatever reason, that's totally cool. This is the direction you're going to have to head. So again, these slightly more, this is more simple mathematically. It does take a little bit more work. Comments, questions, concerns? Okay, flip the page. Let's deal with Ashton's issue. How does this get hard? Well, let me show you. Here's the issue, Ashton. You've got a 3.5 kilogram mass moving at 5.10 meters per second southeast. It hits a barrier and deflects so that its final velocity is 4.2 meters per second, 60 degrees west of south. If the collision with the barrier took 0.52 seconds, what's the force acting on the mass? Well, let's do it. So we'll walk it through step by step. I'm going to zoom this thing in. So if I get off the screen, let me know. But I want to zoom this in so that you guys, I'm going to draw the triangles right on here. So let's start with the equation that we're gonna need here. We've got F delta T is M delta V. This is what we're gonna have to deal with. We're finding the force from a collision. So the impulse equation is the one that you're gonna want to be familiar with. Okay. The easiest way to do this problem is to break these things up into components, just because there's a lot going on here. If you want to try using the other method later, I can happily go through that with you, but the easiest way to handle these are to break the vectors up into components. And then we'll deal with the force in the x direction, we'll deal with the force in the y direction, and then we'll recombine. So if we're going to do that, this is our initial situation. This is our final situation. If I'm going to break this thing up into components, we're going to put a little coordinate grid there. This guy has an x component that way and an y component that way. This thing is heading, we're told, southeast. Due southeast. So what's the angle in there? 45. So let's call this Vx initial. Let's call this Vy initial. And we're going to go over here. I want to figure out what those are. So Vx initial and Vy initial. Our V, we were told, was 5.10 meters per second. So Vx is going to be 5.1 cos 45. And Vy, we can see Vy here is going downward, so I'm going to put that negative in there implicitly. Negative 5.10 sine 45. The beauty of 45 degrees is what? Sine and cosine are the same. The only difference being that negative sign. So this guy is going to be 3.61 meters per second, and this is going to be negative 3.61 meters per second. So those are the velocity vectors. We can do the same thing with the velocity vectors at the end. We're told that this thing is 60 degrees west of south. So that's that angle in there. I've already started to write some stuff down here, so I'm not going to go down here. I'm going to go this way. So that's 60 degrees. What's the angle I'm going to actually have to use? That angle here is going to be this guy, and that's 30 degrees. So this is my Vx final and my Vy final. Vx final, Vy final. Vx final is going to the left, and Vy final is going down. So what do I have to put there explicitly for both? Make them both explicitly negative. We're told that the velocity here is 4.2 meters per second. So this is Vx final is going to become 4.2 cos 30. Vy final is going to become 4.2 sine 30. Those are both going to end up negative. What are those things? What are those expressions? Or the values, sorry, for those variables.
Negative 3.6.
Can we get 2 decimal places for those?
The Y one doesn't have the second, and the second is
Second is 4? Okay. So negative 3.64 and negative 2.10. Okay, cool. So we can see here that the velocity is changing in the x direction and in the y direction. So when we're going to go back to this impulse equation, we're going to break it up into both x and y portions. So this thing is going to become fx delta t equals m delta vx and Fy delta t is m delta Vy. We'll have to do both of those. Because we've broken these things up into components, we can just subtract them directly. Because here we're subtracting Vx final minus Vx initial. Because we've got components, there's nothing special we have to do there. We can do it directly. Vx, the change in time was 0.52. That's going to equal our mass, 3.5 kilograms. And then our V, sorry, I won't put that in. I'll just put the value in there. Delta Vx is final minus initial. So our final Vx is negative 3.64 minus our Vx initial was 3.61. So Vx, force X final is going to be what? How much force was applied to this thing in the X direction? 2 decimal places.
0.7.
Okay. So we found the x, and that makes sense, right? Like the ball was coming into the right, it's now leaving off to the left. That tells us that this wall pushed that way. Negative 48.79 newtons. Conceptually, it makes sense. Let's do the y component. Fy, the change in time is the same, the mass is the same. The delta Vy, that's going to be negative 3.61. Sorry, no, negative 2.1. Negative 2.1 minus negative 3.61. What's our value for that? Okay, let's see if that makes sense.
Oh no!
Sorry, Zach?
Oh, I wasn't.
Doesn't make sense? Why not? Oh, down is negative. But look what's happening here. It was originally going in the y direction with a velocity of negative 3.61. After it bounces, it's only going down with a velocity of negative 2.1. So it was slowed in the y direction, which means it had to have a force acting against whatever its original y velocity was. So what that tells us is this. I'll draw it on here, but I'll actually go solve it down here. Is that we've got a force as our ball hits the wall. There's a force that acts out and a force that acts up, pushing this way off the wall. So I'll redraw it down here. We've got a force, force diagram looks like this. Fx is negative 48.79. And Fy, I shouldn't have drawn it there. Fy is 10.16. So this is going to be our force vector. I can write it a couple ways. Our force, if I'm going to write that in components, is going to be negative 48.79 Newton, or negative 48.79 I hat, plus 10.16 J hat newtons. Or to convert that thing into polar, that's going to equal the square root of 48.79 squared plus 10.16 squared. Our force vector is 49.8 newtons. I believe. And then this angle right there, theta equals the tan inverse of opposite, 10.16 over adjacent, 48.79. Gives us an angle of 11.77 degrees, I think. This direction here is west, that is north, so that's 11.77 degrees north of west.
It doesn't matter. It just goes for
Yeah, because the negatives, yeah. Comments, questions, concerns? It's just stuff we've done. It's just a new application of that kind of stuff. Okay, flip the page. Let's do another one if there's no issues. So that's one object. Let's do the same thing with two objects. So as always, for a closed system, momentum is conserved. This means that momentum is conserved in all directions, x and y. So we've got a 2 kilogram mass moving east at 8 meters per second, hitting a stationary 10 kilogram mass. After the collision, the 2 kilogram mass is moving at 6.7 meters per second, 10 degrees south of east. We want to find out what the velocity in the direction of the 10 kilogram mass is. So this looks a little bit like curling, I don't know, perhaps, assuming that the rocks are different masses, which they're not. So let's write down what we've got for each one of these things. We're going to add the information to the diagram, and then we'll go down and we'll look at how we break this thing up in momentum. So we've got 2 kilograms. We've got 8 meters per second. Because we're now dealing with these things in 2 dimensions, we want to make sure that we acknowledge initial and final velocity in x and y direction. So our mass is 2, our v initial x, and our v initial y. X is 8, y is 0. Our 10 kilogram mass has an initial velocity in the x of 0 and an initial velocity in the y of 0. This is our initial momentum. And we know that this is going to equal the final system momentum. So the 10 kilogram mass has some Vx final and Vy final. We don't know what either of those are. But we do know that the 2 kilogram mass, m equals 2, has a Vx final and a Vy final. We're told this angle right here is 10 degrees south of east. So we can find out what Vx final and Vy final are. This is going to be 6.7. It's going to be negative. No, it's going to be positive. Dang it. The x1 is still positive. 6.7 cos 10. The y, though, is going to be explicitly negative. 6.7 sine 10. So those values are what? It rounded at 6.59?
6.59.
6.60, okay. And the other one is?
Negative 1.
Okay. Meters per second, and this is kilograms. Okay. If my momentum initial has to equal my final momentum, that has to be true in both directions. So my momentum initial in the x direction has to equal my momentum final in the x direction, and my momentum initial in the y direction has to equal my momentum final in the y direction. So we set it all up using the information that we've got now in our diagram. Go for it. Find me, see what you guys can do with this. Find the Vx final, Vy final, and then find the total velocity. And I'll come around and see how things are going. Give it a shot. Just using the momentum equations that we used yesterday. Set it up the way we set it up yesterday. Momentum initial equals momentum final. Well, how much momentum do I have for each object initially in the x direction? That's going to equal momentum finally in the y direction. I'm not convinced those values are correct. Oh, 0.28 and 0.23. Yes, they are. Yeah. Find them individually and recombine.
The velocity forward zero window when it's on the y on. So yeah. Okay. It'll be the inverse of negative 0.28. That's what I got. And go 0.2 over 0.2.
Oh, yeah. Right? Yeah, why not? Yeah, that's good. Oh no, it's this time. We'll work on the example. Who's next? Oh, AJ.
The same question that we went over yesterday in the lesson.
Yeah.
But with the 10 midpoint.
Yeah.
And we did it with summation. I understand most of it, but like, I understand that up till here where we find x initials for like xi.
Yeah.
But then why do we find xi plus 1? Then I understand putting it into the summations and all that stuff for myself, but like, why do we find that one?
Because what you're doing, so this is the x value.
Mm-hmm.
The next x value is what you need is the. Is this for midpoint? Yeah, this is midpoint. Because what you want is the midpoint between 2 points is the average between 2 points. Your xi point plus your xi plus 1 point divided by 2. So going to give you that value for that x point, the halfway point, I guess, here. And then times delta x. Why would we multiply by delta x? That's why you're playing the I plus 1.
Jesus, that's it.
Dude,
Good for you. Turkey, lunch, and dinner. Oh yeah, 3.
hungry boy. That's why you're finding the I plus 1 first.
Okay, so that's only for midpoint.
Yeah. Yeah.
But if you look
No, it should be for any of them.
any
Oh, no. You're right. It should just be midpoint. It should just be midpoint.
Like the back, our assignment for today is to do the x squared function, but find it with the summation from left to midpoint and right here. So, because I'm doing the left hand right now,
Yeah.
so I only need to find.
You're just adding up the function values. I think I need to come back to this question.
Yeah.
Give me a second. Okay, so do we have values for M1, V, M2, V2, X final? Without me having to go through all of this, we should have found that V2 final X, that's that we're looking for. The value of that should be 0.28 meters per second. Have we found this? Okay. So then my V2 final Y, we find a value for that. Carissa, what'd you get? Yep. 0.23. And then we're just going to put this thing back together. 0.28, 0.23. We're going to recombine these things. The square root 0.28 squared plus 0.23 squared. That's going to be 0.364 meters per second. And then that guy there is the angle we want. Tan inverse of VYF is 0.23 over 0.28 is 39.5 degrees north of east. Is the value you should be looking at here. Anybody get something different? You want to see any part of it? It depends why. If you just you're out because you didn't round properly. If you didn't round, that's problematic. Yeah. For V2 final X. Okay. So mass here is 2. V1X initially is 8. This is 0 because there is no velocity in the X direction for our 10 kilogram mass. So 10 times 0. That's going to equal our 2 kilogram mass. The V1X final is 6.6. Plus 10 times V2X final. So that's gone. So it's going to be 2 times 8 minus 2 times 6.6 divided by 10. 2.8 or 0.28. Did you find calculator issue? Okay. Relatively straightforward, yes? Just a little bit of work. Okay. Flip the page. The same example, but now we're going to look at energy. Consider again that same equation. We're going to find the kinetic energy lost in that collision. I'm going to put the values we had for velocity. We had 0.364 meters per second. We had 0.28, 0.23. So this is what, like, because you would never rebuild the question, it would end up looking exactly the same as it did before. 6.6 and 1.16. Do I have it backwards? Yes, I do. Well, thankfully, that's easy to fix. And then you doubted Nathan. Okay, easy to fix. Okay, so this is how the diagram would look after you've solved the momentum equation. You would have all the components in there, and now we say, okay, well, let's go through and solve for the energy lost. Okay, because there's going to be some energy lost when objects collide. We don't know if it's perfectly elastic or partially inelastic. To figure that out, we have to figure out if there was work energy lost. The work energy theorem says this: half mv squared plus half mv squared. So the initial kinetic energies for each object plus whatever work was done, energy lost in this case, is going to equal the half mv squared for one object plus half mv squared for the other. Now, the difference between momentum and energy is this. Momentum is a vector, energy is not. Okay? So because energy is not a vector, we do not use components. Okay? So we're going to go straight to, we're just going to use the actual velocities after they've been recombined. So we're going to have the kinetic energy for 1 initially, plus the kinetic energy for 2 initially, plus whatever work was done is going to equal the kinetic energy for 1 finally, plus the kinetic energy for 2 finally. So this is going to be 1/2 times 2 times 8 squared plus 0 plus work is going to equal 1/2 2 times 6.67 squared plus 1/2 10 times 0.364 squared. Sorry. I had 6.6. Oh, that's why.
I thought it can't be compounded.
Right. Sorry. Okay, so Nathan, it should have just been the 6.7. Nathan,
Come on. You're like
you know what?
on fire.
You're just rolling. Thank you. So what do we get? Oh, now you've said it. He's not going to get it.
I'm sorry. I just screwed everything up.
Work equals what?
Negative 18.45.
Is that rounded?
Yeah.
So what kind of collision is that? Nope. That was not an option. Your options are completely inelastic, partially elastic, or completely elastic. And partially inelastic and partially elastic are the same, so yes. Partially one means you're partially the other, so you're good. Is the glass half empty or half full? Okay, so there it is. This is a partially elastic collision. Easy, yeah? Okay.
What's going on? How do you not see all of it?
How do you know?
Gone. If it was 0, then it's perfectly elastic. If it loses a lot of
If they stick. If they stick, it's completely inelastic. Whatever the value you find for it.
well, but then
That would be the situation in which you lose the maximum amount of energy. When they stick. And you'd have to figure out what the work is. Okay, we're going to skip 5. We could redo 3 again using vector notation? I'm not going to. If you want to see this, let me know. I'll show you later. Okay. Flip the page. Example 7. This says we had, oh yes, but we're not doing all of them. A 200 kilogram lineman moving north at 2 meters per second hits and sticks to a 1 kilogram fullback moving east at 3 meters per second. This, I want you to try for homework.
Like not now.
Like when I'm going to give you time in a second here to do some work. This question is homework. The values are this, because you're looking for the final speed and direction of the pair. V final is, this is what you're looking for, 1.66 meters per second, 53.06 degrees north of east. That's what you're looking for. So this is part of your homework. There's one more example we're going to do. Flip the page. That was a mistake. This page was supposed to go into that blank section. Yeah, it was a bit of a bummer.
A 10 kilogram plate.
Okay, so we've got a 10 kilogram plate at rest on a table. It explodes into 3 pieces. A 6 kilogram piece travels downwards at 4 meters per second south. By downwards, we mean down the page. A 3 kilogram piece travels 4.27 meters per second north of west. We want to find the velocity of the third piece. So I tossed this example in here because we haven't looked at any questions like explosions, and I want you to be able to go through them. The procedures aren't going to be any different than what we've done already. So the first thing we're going to do is draw it out. It's a landmine. Think of it like a landmine. It's a landmine. Landmine sitting on a table, weighs 10 kilograms. The landmine only explodes flat. It doesn't explode up. It just explodes out. Okay? So we've got a 6 kilogram piece. 6 kilograms is just more than half. So good luck drawing this.
Whoa. Exploded so.
Okay, so there's my 6 kilogram piece. Just more than half the circle. It's going, we're told it's going southwards at 4 meters per second. Yeah, this is where the rest of it's going to fall apart. We've got a 3 kilogram section. Okay, we've got a 3 kilogram wedge. We're told it's going. Oh, I didn't give you a direction. It's 30 degrees north of west. So it's going that way. 4.27 meters per second. And this angle down here is 30 degrees. And then we've got a 1 kilogram wedge. Going somewhere. We don't know where, but we've got an idea. It should be generally which way? To the right and probably up. We're not sure. We don't know. It could be perfectly sideways. That depends on the momentum of this piece here. Let's assume it's going that way. And if we're wrong, the components will tell us. So we've got our Vx final and our Vy final. If Vy final is negative, we know this 1 kilogram piece is going down. If Vy final is 0, we know this piece is going purely horizontally. Okay? So the values we find are going to tell us what's actually happening with this piece. Let's do it. We know that momentum initial is equal to momentum final generally. We're going to break this thing up into x and y here in a second, but before we do, what's really nice about this particular problem? What is 0?
They balanced amount of momentum, so, or the initial momentum.
The initial momentum is 0. Doesn't matter what direction you're going in. The landmine is just sitting on the table. Okay? So this is going to be equal to, or your final momentum is going to be equal to 0. Doesn't matter what set of components you're looking at here. So now we're going to break this thing up into x and y. Horizontally, we're going to have 0 equals m1 v1x final plus m2 v2x final plus m3 v3x final. I'm going to label my pieces. We haven't done that yet. That's piece 1. That will be piece 2. This will be piece 3. Just kind of in order of the way the question gives them to us. Which means mass 1 has a velocity of, in the x direction, it's 0. You like that? We don't have v2x final because we haven't broken this thing up into components yet. We go back and we can look at our picture. Mass 2 is the 3 kilogram mass. v2x final, I could break it up here using trig, or I could just use the trig expressions in my momentum equation. It ultimately doesn't matter. This thing is going to be 4.27 cos 30. Yes, and it should be negative. Plus, yeah, because we know it's moving to the left. Plus 1 v3 x final. So v3 x final is what? Which is what, Nathan? You have a calculator in front of you.
Yes, sir. Yes, sir. Okay, that's solid 11.
Someone verify that it is 11.09. Okay? No, it is not negative. Has to be positive. Because our object is this guy. Now we have an x component here. It's 11.09 meters per second. He's hoofing it already. Which makes sense. He weighs substantially less than the other two pieces. So to balance the momentum, they has to compensate with having a much, much higher velocity because it has much, much smaller mass. So our y component still going to equal 0. It's going to be m1 v1 y final plus m2 v2 y final plus m3 v3 y final. And now we can just fill this thing in. Mass 1 only has the y component. So that's what's going to end up going in here. So 0 equals 6. It's going down, so it's going to be negative 4. Plus 3 times the 3 kilogram component is going up and to the left. Up means that velocity piece is positive. So this is just going to be positive 4.27 sine 30 plus 1 v3y final. So v3y final is going to equal 24 minus 6 and a bit. 17.60 meters per second. Can someone verify that? Nathan says it's good. I like 2. 2 is good. Should be positive. Because this negative 24 is going to add over. And this is basically 6. Yeah. Yes, it is. So I put my components back on my diagram. Total velocity is going to be equal to the square root of those squared, because components always meet at a 90-degree angle. We just use Pythagoras. What's the final velocity of our object?
20.80.
What's the direction?
Uh,
57.8 degrees which way? That would be north of east. So we can already see kind of the beginnings of how you could theoretically design an explosive to launch smaller pieces in a direction with a much, much higher velocity. If we could design this plate to break along these lines consistently, you could manufacture something that would shoot 1 kilogram pieces of metal. 20.8 meters per second. 20.8 meters per second is pretty quick. That's a 1 kilogram hunk of metal moving at like between 60 and 75 kilometers per hour. 75 kilometers per hour? That's quick. You're not going to stop that easily with your hands, especially if this is a 1 kilogram slab of metal. Oh, you got to sharpen it on one edge. Now you have a weapon, right? Okay. So this is how the concept of explosives work. Comments, questions, concerns. This was a longer lesson. There's a bunch of examples in here. We'll give you guys some time to play with these. Flip the page. Your homework is this. Okay, it was don't forget example 7 is part of it. I have those ones. Do I want to add anything to it? You're going to do 3. You're going to do 4 and 5. Ooh, yeah, we're going to do 4 and 5. 5 specifies graphical addition of vectors. So try it. Do I give you 6? 6 is good. Yeah, I'll do 6, 8, and 10.
I got 2, I guess.
3, 4, 5, 6, 8, and 10. There you go. That's what we're going to work on for a while here. And then one of my favorite lessons is going to be the second half of class.